Hey guys, today we're going to be learning about the direct comparison test. So basically what this says, or what you have to do is that you have a function and you compare it to another function that's kind of similar, and depending on that you can decide whether the original function is convergent or divergent. So let's say we have let's state the guidelines first. Let's say we have two functions, let's just name it a of n and b of n, right? And b of n has to be greater than or equal to a of n for this to work. Then if b of n converges, then a of n converges too. And if a of n diverges, then b of n diverges too. Note, it doesn't work the opposite way. If a function is larger than the original one and if your original function is larger than your new function that you find out, and the smaller function diverges, that means the original is larger than the new found function and it diverges. But if a function is smaller than the original, if your original is smaller than the function you find and the one that you find converges, then your original converges too. And so let's start off with an example. Let's say the sum of n equals 1 to infinity of n over n squared minus cosine squared. So, a bit of a hint, cosine squared doesn't really change much since it oscillates between 1 and -1, so we can kind of ignore that. And so we have here and so we can rewrite it as the sum of n equals 1 to infinity of n over n squared, which also equals the sum infinity n equals 1 of 1 over n. Okay, so in this scenario we have found the equation that we're going to compare to, which is 1 over n. We'll say that 1 over n is 1 over n equals a of n, and n over n squared minus cosine squared n equals b of n, since this would be larger at most values of n. And so we see now that since 1 over n, which is a harmonic series, diverges, you know that the original is going to diverge too, because this is larger than that function there. So we can say that this diverges by the direct comparison test. Let's try another example. We have here the sum n equals 1 over infinity of, say, n squared plus 1 over n to the 4th plus 1. Alright, so now we have to find a function that is either smaller or larger, and or what is most similar. And you can kind of ignore the 2 and 5 since they don't really change the functionality that much. So we can just say that kind of looks like n squared over n to the 4th, which is 1 over n squared. So that is the equation that we've found. And if you plug in values, you can figure out that that 1 over n squared would be larger than n squared plus 1 over n to the 4th, because actually, let's change the example a bit. Let's make that n fourth plus 2. And okay, so we know that let's see, sorry about that. 1 over n squared is 1 over n squared is smaller, or no, n squared plus 1 over n fourth plus 2 is smaller, so that equals a of n, and so that's set equal to b of n, and since a of n is smaller than b of n, and, or whoops, let's set around, my bad. And you know that 1 over n squared is a p-series, so you know that that converges, and since the original function is larger, you know that the original function converges too, so it's going to converge by a direct comparison test. Thank you for watching.